All right, good morning, good afternoon, good evening, whenever you listen to this video. I hope you're doing well. Hopefully better than me. I just got through about half of this, which took about an hour, and realized it didn't save. So I'm going to try to save this more in parts. I think we have, let's see here, about 24, so I'm going to try to do 6 questions per video here to try and break this up. So what I've given you here is what I know about the air test, which isn't a whole lot. I've told you guys that before. There just isn't a whole lot of information out there quite yet, being in the first phase of the air test. And so as we look at this air test here, understand that I am pulling information from what is considered the Florida test. And hopefully that's going to be enough information to give you guys confidence and do well on your test as well. So first of all, let's go ahead and take a look at what we have here. This is the Florida State Assessment. You can see that right here, Florida State Assessment Mathematics Reference Sheet. I'm assuming that Ohio's will be similar as well, but you've got some basic conversions on the front side, and then you've got the geometry formulas for sine, cosine, and tangent, which hopefully you guys have those memorized already. And then we've got some volume formulas which we have not covered, and then we also have the slope-intercept form and then the point-slope form, the equations that we have there. Now, I'm not going to go over slope-intercept or point-slope form. I'll probably review those as we get going here. There's only one problem that I've seen so far that deals with volume, which is good since we haven't gotten to it this year. But so I want to just do something real quick here and kind of get you caught up with the volume formulas. This first formula here is the volume formula for a prism or a cylinder. Why is it for a prism or a cylinder? Because the volume of those two shapes are similar in the fact they both have two bases. Okay, so this is for prism / cylinder. Okay, and so this capital B, whenever you see a capital B, that's referring to the base area. So if I'm going to go ahead and give you like a hexagonal prism, both bases are hexagons, so you have to find the area of the hexagon, which you guys know how to do, and then you're going to multiply that by the height of the prism. Now the height here and the height here, okay, is the distance between the two bases. Distance between two bases. Okay, and so that length is going to be your height. Now the second volume formula that we're looking at here is for a pyramid, or I don't know why I put an E there, pyramid or a cone. Okay, and why do they have the same formulas? Because they have one base. Okay. Now, I probably shouldn't have put this arrow up here. There's not two bases in a cone or in a pyramid, okay? And so we're actually going, the height is going from the base, I'll draw a cone because that's probably easiest, is going from the base to the vertex like that. That would be considered the height of the cone. Okay? This last one, and I want to make sure you draw your attention to the cube right here, okay? This is for a sphere, volume for a sphere. So just something to keep in mind. You want to keep that reference sheet with you. One thing I've noticed is that I haven't noticed a whole lot of conversions in the test that I looked at, but what I did notice is that they ask you to answer to the nearest tenths place, stuff like that. So make sure you're being specific when you do that. All right, now the next thing we're going to do is we're going to look at these first 5 problems here, first 6 problems, okay? And this first one, I'll just tell you this. Hopefully you can see these pictures a little bit better than they are up on my screen, but they will be clear when you get to the actual test. And when it comes to these type of problems, you really need to get these fully correct, okay? You don't have to get all the problems correct on a standardized test. Just get the ones that you know how to do correct, okay? So as I look here, what do we have? Well, we have a cylinder on the bottom of this first one, and a cylinder over here. Okay, and then you have a cone on top and a cone on top. Okay, so we've got those two objects. That one's pretty simple. Here's what you have in the next one. You have a cylinder over here, cylinder over here. Same thing with those two right there. So you got the cylinder there. And then these connecting walls, you have to think three-dimensionally when you look at this picture here. So if I was to go ahead and draw it, you've got these three cylinders. And you've got this other point over here. And so basically, okay, well, what is that? I'm looking down from above. This is going to end up being a prism. Okay, so a rectangular prism. And we see that answer over there. This next one actually made me think a lot when I looked at it initially. And so make sure you do that. It's kind of hard to see, but this right here is actually a cone because the base is spherical. Okay, not spherical, circular. Okay, this right here is going to be a cylinder. Likewise, this will be a cylinder. Okay, so you got two cylinders there. You've got this right here. Okay, now it's going to be a pyramid, okay, probably a square pyramid up there on top. So that's where the pyramid comes from. And then if you want to look at this tower, okay, what is the tower? Well, the tower is going to be a rectangular prism, and you can even look at the entire building here as it works its way back, okay. It's also going to be a rectangular prism, okay. So just something to keep in mind there. That last one actually takes a while to see there, but make sure you can see those there. All right, now looking at the next problem. As we look at the next problem here, this is a concept that we are going to cover here in a couple of days, and so I want to make sure, one, make sure you know what you're looking for as a final answer. Don't give your answer down here to something that was part of the problem but not the full answer. One other thing to think about, this is the PDF version of the test. The test you guys are going to be taking is going to be online, so make sure that you get a chance to look online. I'm going to try to give you a look-see as to what that's going to be like. But here's the concept that's being covered in this problem. Whenever you have two chords intersecting within a circle here, they form an angle. And that angle has a relationship with the two intercepted arcs, okay? That relationship is that the angle formed is the average of the two arcs that it intercepts. Okay, so you can actually go ahead and pause your computer and take a moment to go ahead and solve for x there. But once you have x, don't forget to figure out what angle AEB is going to be. If I were to go ahead and solve for x, here's what I would have done. Subtracting 1x from both sides, dividing by 3. That's what x is going to be. Now, if I plug that x in over here, I have 80 is my value of that angle. I have to find this angle right here. Well, together they form a straight line, so if I take 180 minus the 80, you get your 100 degrees, which is giving you the answer down there, okay? So again, don't forget, again, we'll review this, but the angle formed inside the circle is the average of the two intercepted arcs. It's a basic concept, don't forget that. Okay? All right, now, the next problem, number 3. Okay? This is one of those problems there that I'm probably going to go ahead and try to encourage you guys to get your graph paper out when you take the test and to go ahead and graph all possibilities here. And so if you read over the problem, basically what we want to do is figure out what the translation is going to be, what reflections have to take place in order to come up with this translation. The translation is 4 units to the right and 4 units up. So if I do that, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. There's S. 1, 2, 3, 4, 1, 2, 3, 4. There's T. And then R, 1, 2, 3, 4, 1, 2, 3, 4. Okay. And so what we want to figure out is how do we get to this triangle right there? Well, how we get to that point is we're going to use these translations down here. Now, I'm going to show you the quickest and easiest way to do this because there's 16 possibilities between these two down here. And the easiest way is to go ahead and start off with the very first one. Take your time with it, and I think you'll figure it out real easily. And that's this. If I go ahead and graph x equals 4, okay, taking just one point, s, 1, 2, 3, 1, 2, 3, I put s right there. Now I'm going to use one of the equations from down here, y equals 6. Y equals 6, going up, 1, 2, 1, 2. Okay, obviously point S isn't at the same location, so it doesn't work. If I take y equals 8, now I'm moving down to this next equation here, y equals 8, I go back down to my second point, and I go up 1, 2, 3, 4, 1, 2, 3, 4. Look at that, it's not in the same location. If I do negative x plus 10, remember graph your y-intercept first, okay? Maybe I should start to use a different color here so we don't get confused, okay? And negative x down 1 over 1. Okay, as you look at that, I'm going to go a half and a half. Well, those aren't the same locations there, so that's not going to work either. And then if we do plus 12, negative x, plus 12, that point right there, down 1 over 1. Okay, now this time I'm going to go up right there. So, well, what I've just proven to you right there, and I know that was really fast, but I hope you caught on to it. I took this letter A right here and compared it with all the other equations up there and showed you that that's not going to work there. Okay. Now the next thing I'm going to do, I'll take the next equation. Oh, went one too far. Okay. The next equation is x equals 6. So if I do x equals 6, here we go. Over 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's s. From there, x equals 6. So it's that line right there. Or y equals 6. So I'm going to go up 2 more. Okay, obviously not the same position as s. If I do y equals 8, 2, 4, up 2, up 4. Okay, obviously not the same location there. If I do the diagonal, plus 10 and negative x. Here's what we have, 1, 2, half, 1, 2. Obviously not in the same location. And so, you know, I'm just trying to get you to see all these possible places that S could be. Now, to prove to you that that last part, letter D, okay, letter D and letter C will be correct. Here's how it's going to be. I have negative x plus 6, so plus 6 and negative 1 over 1. Okay, if I graph that half and half, 1 and 1, 1 and 1. Okay, so this would be S, T, and R. Okay, and then from there we have plus 10 and negative x. Okay. 1 and 1, we see T is in the same location. 1 and a half, 1. S is in the same location. 1 and 1. R is in the same location. So again, that's why those two are going to be the correct answers there. Now, is the same as the translation because the lines are, now you can tell, they both have the same slope here. Okay, negative x, negative x. And so maybe I'd make a note on my paper here. Same slope equals parallel. Okay, and then opposite reciprocal equals perpendicular. okay? And again, remember an example of this. If I give you a negative 3/2, the opposite of that would be positive, and the reciprocal would be 2/3, okay? So that would be an example of perpendicular slopes. I could also give you a positive 5. Remember, that's 5/1. The opposite reciprocal would be negative 1/5, okay? So just keep that in mind there. That's how I would do that problem right there, checking out all possibilities there, okay? All right, let's look at the next one. Side note, I can't stand how sloppy this pen writes. Love the board, can't stand how sloppy it is, okay? All right, so number 4, Johnny wants to find the equation of a circle with the center at 3, -4, and a radius of 7. He uses the argument shown. Choose the correct word or phrase to fill in the blank with the argument. For each blank, fill in the correct circle before you use the phrase that is correct. All right, the circle equation. The circle equation is this: x minus h squared plus y minus k squared is equal to radius squared, okay? Why is that the equation? I'll explain it to you in more detail in class, but what it is if you can picture this part right here is a squared, this part right here is b squared, this part right here is c squared, okay? And basically, that formula comes from the Pythagorean theorem, also the formula that we talked about earlier on this year. Okay, the distance formula also comes from the Pythagorean theorem. However, instead of using the square roots, okay, this one doesn't have a square root in it. Why is that? Because they squared both sides, so we have this right here. Okay, and so hopefully that makes sense to you. All of those formulas are derived from the same point. Why is that? The definition of a circle is the set of all points a given distance from a given point. And how do we show that? Well, we're going to use the Pythagorean theorem, the hypotenuse being the radius, and you can rotate that all the way around the circle, and that's why we use that equation. So as I use my information here, this is my h and my k, h, k, and so we have x minus h squared plus y minus k squared is equal to the radius squared. The radius was given to us right there, okay? So if I simplify this up, there's nothing to simplify in the first parentheses. However, the double negatives can become positive, okay? And so as you look, I don't know why they use the absolute value brackets there. I just know that they did that. Don't let that throw you off your game, okay? And so from there, we're just putting in what we have inside the parentheses. So the last part says this: the blank can now be used to create the equation that shows the relationship between the horizontal, vertical, and total distance of x and h to the center of the circle, okay? Like I was saying before, I'll try to explain this a little better right here, okay? If you have a circle, okay, consider that's a really nice circle. I know it's not, okay? If I go ahead and draw in the Pythagorean theorem here, okay, this radius length, I draw it in here. That radius length still doesn't change as I go all the way around, okay? And so, because we can use that Pythagorean theorem, whatever this length is, gives me the radius length, okay? That radius length always just stays the same, okay? And so as a result, that's why we use it. It's the set of all points a given distance from a point, okay? All right, looking at the next one. Number 5. Now this one, I'm going to be honest with you, I put a big question mark on it because I think that either Florida messed up or they've done something that doesn't accurately depict what the question is trying to ask. So here's what it says: regular pentagon with the points E, F, G, H, I, center at K. Remember, regular means all sides and angles are congruent, okay? select all the transformation that carry the figure onto itself. Now it says onto itself. It means that these vertices here have to go in the same location as another vertex. So F doesn't have to remain where F is, but F has to be either in points E, I, H, or G's location. And that's where things get a little frustrating for me. So the first one is correct, because if I go ahead and reflect it across line EK, okay, line EK going through both those, E remains on itself because it's on the reflection line. I goes to F, F goes to I, H goes to G, G goes to H. That makes complete sense to me. Okay, so that part is correct. Now the next part says this, 180-degree counterclockwise. Now, please don't get this wrong. I have no idea why that just happened. Don't get this next part wrong. When we rotate something counterclockwise, it's against the clock's rotation, so, oh boy. I'm going to try to pause this and figure out what I did. All right, well, whatever I did, it's gone now, so hopefully it stays gone. The second part of this is the part that I don't understand. 180-degree counterclockwise rotation. Again, we're going against the rotation of the clock, so we're going this direction right here. Okay, about point K, and let's talk about that. 180 degrees counterclockwise rotation. So if I'm starting at point E, 180 degrees about point K puts me over in position right there. Okay, that doesn't map back onto itself. I have no idea why. They choose this as part of the answer. If I do I, 180 degrees counterclockwise, putting I right there, H will go over here, G will go over here, and F will go over here. So it will look something like this. Okay? It doesn't map back onto itself, so I don't know why it's included as part of the answer. Okay? If you guys think you have some insight into that, let me know, but that's how I read that problem. And then the second part, or the third part, reflection across the vertical line through point K. Again, I don't know why it's saying it's mapping back onto itself, because I would then be here, H would be over here, E would be over here, G would be over in here, and F would be over in here. So it would look something like this. Okay? So again, it doesn't map back onto itself. Yes, it's on itself, but to be onto itself, it has to be in the same vertices. So maybe what they're implying, and I think this is a poor use of the definition of onto itself, is that the center remains still the center. And if that's the case, then that would be true. Okay? And so maybe we should use that as our definition moving forward. A 90-degree counterclockwise rotation about point E. Okay? Well, 90 degrees counterclockwise, okay, again, we're going this direction, about point E. If I go ahead and do 90 degrees from point I, that same distance, so I would be out in here, 90 degrees, that's not 90 degrees, I'll put it right there. That would be H, G, G would be somewhere in there, F would be somewhere, nope, that's not right. F would be somewhere in there, and then E remains the same, so we would have something that would look like this. Okay? And in that case, if we use onto itself as the definition, it wouldn't be onto itself because K doesn't remain the center point. So, letter C, reflection across line FI. Line FI, reflection across that. Well, K gets moved, so that's probably the biggest thing. If I move E, somewhere up in here, H would be over here, G would be over here, F and I remain in the same spot. So it would look something like that. Okay. So again, it's not onto itself. So maybe we're onto something there, that's the definition that they want us to use. K has to remain in that same location. So in the next one, a reflection across a vertical line through point K, we talked about this one already. K does remain in the same spot because it's on the reflecting line. And so, we've already proven that one. 180 degrees clockwise rotation about point K. Again, K will have to remain the center point because we're rotating about that. So I guess that would carry K back onto itself. And then a reflection across line EK. Line EK, this is on the reflecting line, so these points remain there. Those two switch, those two switch. So yeah, I guess I figured it out. So 180 degree clockwise rotation about point E. Well, if we look at this one, point E, 180 degrees. If I go with, well, let's just do this right here. 180 degrees, clockwise or counterclockwise, it doesn't matter, it's going to remain in the same spot. So there's point K, obviously not back onto itself. If I was to do I, there's I, there's F, there's G, and there's H. So it would look something like this. Okay? So, yeah, I think we may have figured that one out. So, when it says onto itself, make sure that the center point has to be onto itself. I've always known onto itself, meaning the vertices are back onto itself. So, all right, let's look at one more problem here, number 6. Okay, number 6, here's what we have. We have a circle, okay, that's been divided up into 8 equal sections, okay? And they took those 8 equal sections and they laid it out here, just like this one, all right? Now, what I want you to notice, there's 2 things. This length right here is the same as this length over here. I'll change my color real quick, okay? That's a radius, this is a radius, okay? This length right here, 1, 2, 3, 4 humps. 1, 2, 3, 4 humps. That's a half distance around the circle. So this is actually 1/2 the circumference of the circle, okay, to there. All right, and so as we look down through here, the height of the parallelogram is, well, hopefully you read the whole problem. The height of the parallelogram is approximately equal to the circle's diameter. Well, that's not true because we already proved that. The area of the parallelogram, which remember is going to be base times height. Okay? Now the base would be this length here, half the circumference. The height would be the radius. Base times height. That works. Okay? The length of the parallelogram is approximately equal to the circle's circumference. Well, the length we said isn't the circle's circumference, it's half the circle's circumference. Okay, the radius of the circle is approximately equal to the height of the parallelogram, and we already proven that. Okay, and then the area of the parallelogram is approximately 8 times 45 over 360 times pi r squared. In this problem right here, I would go ahead and multiply these two together and see what you get. If you can't do that in your calculator, here's what we have. 8 times 45, 360. 1 times 360, 360. What's 360 over 360? It's 1. These cancel each other out. There's the area that we're looking for, pi r squared. Okay? All right. With that being said, I'm going to go ahead and stop this, and hopefully it'll save this time, and we'll move on to the next video.